Welcome to the tutorial on our package metasens. I'm Guido Schwarzer, and I'm the maintainer of the package. You find the R script here and the dataset on Zenodo. So let's start. There are basically two versions of metasens available. One is the official CRAN version, and the other one is available on GitHub, where you can find bug fixes and newer features. So let's start by looking at the overview page of metasens. Here you can see that metasens provides some advanced statistical methods to model or adjust bias in meta-analysis. And it also supports our book, Chapter 5. It is an add-on package to Meta, which provides basic methods for meta-analysis. And here are the basic methods that are available in metasens. And I will talk about the first three here in this tutorial. So let's start with the limit meta-analysis. So this method has been published in Biostatistics. Main work was by Gerta Gürker, together with other colleagues from our team in Freiburg, and also James Carpenter from the London School of Hygiene and Tropical Medicine in London. The starting point of this method is the standard random effects model. The equation for that is given here. And what we do in this method is we extend it by introducing this parameter alpha R, which models potential small study effects, or which are often called bias, publication bias, selection bias. And by introducing this parameter, also the meaning of the intercept of the beta R changes here, because now in this model it is the treatment effect adjusted for small study effects. Then in the next step, in order to get some estimates for this, we consider a setting where we increase the precision of the individual studies, and we increase it by using here this M as a factor in order to increase the precision, so to reduce the variance here. And then the limit method starts by going here with this factor M to infinity. Here we already get the equation for this, but at the end, if we plug in our estimates and so on, we get then this equation here, which we will call limit meta-analysis. And we have here the study-specific treatment effects, which can be interpreted as new study means adjusted for small study effects, and they are shrunken to a new common mean, and that is then our estimate. There is a link to empirical base estimates, which are described here in this publication, but I will not go into detail. Instead, let's go back to RStudio and have a look at the help page of limit meta. So here we see the arguments of the function. There are not that many, and what we can see is that most of them have defaults coming from X, and X is an object of class meta. So for that we are using then the meta package. Okay, before we get to the limit meta-analysis results, let's first dig into one meta-analysis example, and this is here an example which is available in the metasens package. It's on the effectiveness of some painkillers, abbreviated here NSAIDs. They were applied in patients with acute pain and compared to placebo, and here the outcome was the reduction in acute pain of at least 50%. So this is the more 1998 data set. If we look here at it, we see we have the study IDs. the number of successes, so reduction in pain of at least 50%. Dot E means this is the experimental group, so the NSAIDs group, and dot C is the comparator, and the comparator here was placebo. And then with MetaBin, we can conduct a meta-analysis with binary outcomes, and we use here the odds ratio as the summary measure. If we look here at the results briefly, we can see first that there is a large effect here of NSAIDs compared to placebo to reduce pain. However, we see that the results for the common and the random effects model, they are quite different. So we have the more extreme result for the random effects model. And this is due to smaller studies having different, larger results, treatment effects, than the more precise the studies. And we see here is quite some heterogeneity in these 37 studies. Tau squared estimate is here about 0.49. We come back to this if we look at some other methods later. So, and if we look here at the funnel plot for these 37 studies, we see that this is here clearly asymmetric. So these very large odds ratios we only observe in the smallest studies. But if we go up here, we see that the larger studies are, scatter around here on a large range here of values, but overall we still get the impression that the treatment works here. So then let's, in the next step, use trim and fill, which is part of the meta package, so part of the basic functionality. And if we run here this trim and fill analysis, we see that trim and fill adds 14 studies to our 37. So in total, we have then 51 studies. Odds ratio here is clearly reduced from 3.7 down to about 2.5. However, what we also see here is we have a much larger between study heterogeneity estimate, increasing from 0.49 to 0.92. And the reason for that is quite clear if we look here at the funnel plot for the trim and fill method, because what we see here is that the most extreme studies here from the right side are mirrored here on the left side. And we have here this typical gap here in between, in the middle, for the trim and fill method. But overall, we add here heterogeneity by adding the most extreme results. And this is the property of the trim and fill method. And we also did some simulation studies showing that other method, especially the limit meta-analysis method, works in generally better. In order to run it here, we again use just here as an example the meta-analysis object that we created before. And in the printout, here's the full printout of a limit meta-analysis. We see that we get here both the unadjusted estimate, that's just the same as we had before, and the adjusted estimate, and which is very much decreased here, so down to 0.85. Still significant, so we still would say that there is clearly a positive effect of NSAIDs compared to placebo to reduce pain, but it's clearly not as large as based on the original meta-analysis. What we also get here are tests for small study effects and also tests for residual heterogeneity after accounting for this small study effect. And we see that there is still some residual heterogeneity. What the model actually does is visible in the funnel plot. Here, the funnel plot, we show the diamond, the width of the diamond corresponds to the lower and upper confidence limits for the adjusted effect here at top. So this is here the adjusted effect, so in the middle of the diamond. And we see here the regression line, the underlying regression line here plotted in the funnel plot. and it's not a straight line because we use here some transformation in the regression of these two quantities, so of the treatment estimate and its precision. But the line clearly shows here that we can nicely with this limit meta-analysis follow here the information from the smaller studies, the more biased studies, to the larger studies which are less biased. Yeah, that's it basically on the limit meta-analysis method. Then let's move on to the next model or method. That's the COPAS selection model, which is provided in the COPAS function. Actually, before metasens, there was a COPAS package which we developed some 15 years ago, and so the idea at that time was to just have for the COPAS model, which is quite complex, as you will see in a minute, to have for that a separate package which is not part of the base meta package. So this model goes back to COPAS and Xi. John COPAS had a couple of publications in the early 0 years on sensitivity approaches based on selection models to tackle publication bias or selection bias, as he often called it. And again, the starting point here, the so-called population model, is a standard random effects model, here written down in a different way, but this is just the same model as for the limit meta-analysis. And what is also considered here for the COPAS selection model is a model for the publication probability or the selection probability that a study is selected for a meta-analysis. And this is assumed to be based on the reported standard deviation of the study, so of the precision of the study. And the probability is modeled via this standard normal cumulative distribution function. There are two parameters, A and B. A is controls the probability that a study is selected in general, so the overall proportion, and B models how fast the proportion increases as the precision the precision increases, or as the standard deviation gets smaller. And this model can be written down here in a different way, and then at the end we come to the combined model, so a model for the treatment estimate, the first two lines, and then also a model for the selection process. And these two equations are interlinked by a correlation row, and so this is how in this model we can introduce selection bias. And a row of 0 would mean that the probability of selection, probability of a publication of a study, is not related to its precision, and if row is different, then accordingly this is different. And so we have a model here with in total 4 parameters, 5, sorry, mu, tau squared, A, B, and rho. And as this is not, we cannot from the information we have estimate all of those. What we typically do is we assume a grid of values for A and B, which are also sometimes called gamma naught and gamma 1 in other publications. And this is how we approach this. Then let's look again at the help page, and we see here again there are a couple of arguments. The first argument, x, again is an object of class meta, just as for the limit meta function. Again, there are some arguments which take values from this meta-analysis object, and the values for A and B, or gamma naught, gamma 1, can be defined here using these two values here. And To run the model, we again just as a single input can use here the COPA, the meta-analysis object. And then if we plot it, we see here 4 plots. Again, our funnel plot. Then here a contour plot which has these values of A and B, or gamma naught, gamma 1. And the contours here in this contour plot correspond to the estimated treatment effect, or the adjusted treatment effect, because here at the top right corner, we do not account for selection bias, and the further we go down the line, the more we account for it. And here we can see in a similar way, if we go down this line, what is the influence on the confidence interval. And here at the bottom right figure, we can see, okay, if we adjust for bias to a certain degree, is there still some residual selection bias or not? And as we can see here, this is the case for all values here. Accordingly, if we look at the printout for this model, we see that we do not get an adjusted estimate, because again, if we go down here on this line, all values that we get here, the test for residual selection bias is still significant. So what we do then here, or can do, is we specify values for gamma naught and gamma 1. And if we do this, then we get here, with the last estimation here, or the last point, we have an adjusted estimate where we do not see any residual selection bias any longer. And accordingly, here in the printout, we get here an adjusted estimate, and this is just here the last line in that case. Good, then just very quick, let's go to the last model here, which is here this upper bound for outcome reporting bias. The publication for this is again by John Copas, and in this case Dan Jackson. What they proposed was a bound for publication bias, so a setting where the number of studies that are missing is unknown. However, there was a couple of years later a publication by Paula Williamson and Carol Gamble that used this method for outcome reporting bias. And here the advantage is that for outcome reporting bias, we know for our meta-analysis how often do we have the information in a study for an outcome, and how often we do not have it. And so there we have a number of studies that we can easily use in our analysis to see what is here the maximum bias for a given number. And this is here in for this ORB bound function, the second argument, this case suspect argument. But for publication bias, we have the problem that we do not really know this number. And therefore, if we do this here, this method for our example, we do not know what is the correct number here of unknown studies. And here in the second example, I'm looking here at a scenario again for our NS8 meta-analysis, where we assume that there are up to 10 studies missing. And we can see here that the odds ratio is going down, but the problem is we do not know the correct number here. So therefore, this method nowadays is used for outcome reporting bias, but not for publication bias. Yeah, and then in the script, you will find also an example here for the last method that I have no time to talk about. So for these imputation methods for missing binary data. But I hope that by this tutorial, you got a quick introduction into the metasens package, and you see that it's quite easily to use. Thank you for your attention.